Welcome to the Crevice Corrosion channel. My name is احتشام زاده. I'm a researcher in the field of corrosion and protection of materials. Chapter 3, Section 2, Types of Corrosion. Crevice corrosion, pitting corrosion, pitting factors, alpha and beta. Crevice corrosion, known as underdeposit or gasket corrosion. 1. This type of localized attack is usually associated with small volumes of stagnant solution caused by holes, gasket surfaces, lap joints, surface deposits, and crevices under bolt and rivet heads. 2. The deposit acts as a shield and creates a stagnant condition thereunder. 3. This figure shows gasket corrosion on a large stainless steel pipe flange. Mechanism of crevice corrosion. 4. To function as a corrosion site, a crevice must be wide enough to permit liquid entry but sufficiently narrow to maintain a stagnant zone. 5. For the above reason, crevice corrosion usually occurs at openings a few thousandths of an inch or less in width. Although metal ion and oxygen concentration differences exist during crevice corrosion, these are not its basic causes. The basic mechanism is autocatalytic. Consider a riveted plate section of metal M immersed in aerated seawater, pH equals 7. The overall reaction involves the dissolution of metal M and reduction of oxygen to hydroxide ions. Reduction, oxidation. Oxygen reduction produces hydroxide ions. Oxidation M produces Mn plus M electrons. 8. Initially, these reactions occur uniformly over the entire surface, including the interior of the crevice. Charge conservation is maintained in both the metal and solution. Therefore, the rate of corrosion within and without the crevice remains equal. 9. After a short interval, the oxygen within the crevice is depleted because of the restricted convection, so oxygen reduction ceases in this area, an important indirect influence of oxygen depletion. 10. Oxygen depletion becomes more pronounced with increasing exposure. After oxygen is depleted, no further oxygen reduction occurs, although the dissolution of metal M continues as shown in the figure. 11. This tends to produce an excess of positive charge in the solution, which is necessarily balanced by the migration of chloride ions into the crevice. 12. This results in an increased concentration of metal chloride within the crevice. 13. Except for the alkali metals, for instance sodium and potassium, metal salts, including chlorides and sulfates, hydrolyze in water. NaCl plus H2O equals MOH plus HCl. 14. This increase in the solution increases migration, and the result is a rapidly accelerating or autocatalytic process. Formation of oxygen concentration or differential aeration cell is shown in this figure, and formation of a metal ion concentration differential cell is shown here. Both chloride and hydrogen ions accelerate the dissolution rates of most metals and alloys. These are both present in the crevice as a result of migration and hydrolysis, and consequently the dissolution rate of metal is increased. Crevice corrosion, an autocatalytic process. 15. The fluid within crevices exposed to neutral dilute sodium chloride solutions has been observed to contain 3 to 10 times as much chloride as the bulk solution and to possess a pH of 2 to 3. This table shows the effect of geometric and electrochemical parameters on crevice resistance. Increasing critical anode current density, IC, causes crevice corrosion resistance to decrease. Increasing crevice width causes crevice corrosion resistance to increase. Increasing passive potential range EP causes crevice corrosion resistance to increase. Increasing active potential range EA causes crevice corrosion resistance to decrease. Increasing solution-specific resistance ρ causes crevice corrosion resistance to decrease. The video entitled Chapter 5 Section 1 Active-Passive Alloys, in which IC, EP, and EA are explained, is available on this channel. 17. As the corrosion within the crevice increases, the rate of oxygen reduction on adjacent surfaces also increases. Slide number 87. This cathodically protects the external surfaces. 18. Thus, during crevice corrosion, the attack is localized within shielded areas, while the remaining surface suffers little or no damage. 19. There is often a long incubation period associated with crevice attack, 6 to 12 months or more. However, once started, it proceeds at an ever-increasing rate. 20. Metals or alloys that depend on oxide films or passive layers for corrosion resistance are particularly susceptible to crevice corrosion. Combating crevice corrosion. A. Use welded butt joints instead of riveted or bolted joints in new equipment. Sound welds and complete penetration are necessary. B. Close crevices in existing lap joints by continuous welding, caulking, or soldering. C. Design vessels for complete drainage to prevent solids from settling on the bottom of the vessel. D. Inspect equipment and remove deposits frequently. E. Remove solids in suspension early in the process or plant flowsheet, if possible. F. Remove wet packing materials during long shutdowns. G. Provide uniform environments, if possible, as in the case of backfilling a pipeline trench. H. Use solid non-absorbent gasket such as Teflon wherever possible. I. Weld instead of rolling in tubes in tube sheets. Ranking of some alloys in U.S. Navy tests for resistance to crevice corrosion in filtered seawater at 30 degrees Celsius. Number 1. Hastelloy C276 and Inconel 625, Crucible, Ferrarium, Hastelloy, Haynes, and other alloys. For example, Ferrarium is a super duplex grade of the duplex stainless steel class. Pitting corrosion. Pitting is a form of extremely localized attack that results in holes and cavities in the metal. 2. Pits are sometimes isolated or so close together that they look like a rough surface. 3. Pitting is one of the most destructive and insidious forms of corrosion. 4. Pitting is also difficult to predict by laboratory tests. Reasons are explained in the slides number 97 and 98. 5. Pitting is particularly vicious because it is a localized and intense form of corrosion, and failures often occur with extreme suddenness. Morphology of deterioration in pitting corrosion. Narrow, deep, elliptical, wide, shallow, subsurface, undercutting, horizontal, vertical. 6. Pitting and under-deposit corrosion are the most observed types of corrosion in MIC, microbiologically induced corrosion. In this figure, a scanning electron microscopy (SEM) image of pitting corrosion caused by MIC is shown. 7. This type of corrosion often goes undetected as rust covers the pitting, rendering it unnoticeable. 8. The reason pitting corrosion is very common and unpreventable in steel reinforcements is due to difficulty in designing pipes to combat this effect. 9. The process inside the crevice is essentially the same as the propagation of pitting, and autocatalytic nature of pitting is exactly the same as crevice corrosion. 10. This phenomenon involves two steps: A. Pit initiation, B. Pit propagation. 11. If for any reason the rate of metal dissolution is momentarily high at one particular point, for example inclusions, surface scratch, and emerging dislocation or other defect, or random variation in solution composition, pit initiates in many points on the surface. 12. The mechanism of pit growth is virtually identical to that of crevice corrosion, and all of the 20 tips mentioned in the slides 83 to 89 that are based on formation of stagnant zones in the stable pits and migration of chloride ions are valid for pitting corrosion. An example for pit initiation mechanism in the industrially produced quenching and partitioning martensitic stainless steels. Schematic illustration of the pit initiation mechanism at MNS and TIN inclusions in the alloy 3CMN was shown by Gaji Li et al. In 2024, Electrochemical Acta, Volume 498. Stage 1. The MNS inclusion causes discontinuity and less heterogeneity of passive film. The well-known MNS inclusion triggered localized corrosion. Stage 2. Dissolution of MNS inclusion and trenching of the TIN matrix interface occurs. This is driven by the 40 mV surface potential difference. Stage 3. When the trench grows deeper, a stable pit forms. How to predict an equipment life that is susceptible to pitting corrosion? There is a statistical variation in the depth of pits on an exposed specimen or normal or Gaussian distribution. The average pit depth is a poor way to estimate pit damage, since it is the deepest pit that causes failure. Measurement of maximum pit depth would be a more reliable way of expressing pitting corrosion, but such measurements should never be used to predict equipment life since pit depth is also a function of sample size. Pit depth as a function of exposed area. This figure shows the relative probability of finding a pit of a given depth as a function of exposed area. For example, there is a probability of 20% of a pit with a depth of d occurring on a sample with an area of 1. On a specimen 4 times larger, it is a virtuous certainty probability equals 100% that a pit of this depth will occur, and a 90% chance that a pit twice as deep will also occur. On a specimen 6 times larger, it is a probability of 100% that pits of depth d, 2D and 3D will occur. Therefore, attempts to predict the life of a large plant on the basis of tests conducted on small laboratory specimens would be unwise. Challenge number 6. Differences between crevice and pitting corrosion. If you like to challenge yourself, please answer this question in the comments down below. In what aspects are these two types of corrosion different from each other? Determining pitting factors using 3D scanning technology and matrix laboratory case studies in construction materials. Zhou et al. In 2018 showed distribution of pitting factors alpha and beta along the bar length with different mass loss ratios, where M0 is the mass of the initial 250 mm steel bar and M1 is the mass of the corroded 250 mm steel bar. Mass loss ratio is eta equals M0 minus M1 divided by M0. 3D scanning technology was used to obtain the pitting corrosion data of corroded steel bar. Figure compares the distribution of corrosion depth along the bar length at 3.41%, 5.85%, and 30.22% mass loss ratios, explaining the tendency of maximum corrosion depth along the length of the steel bar. The vertical axis here shows corrosion depth, and the horizontal axis shows length along the bar. Eta is 3.41% for the data shown in black. Eta is 5.85% for the data shown in red, and eta is 30.22% for the data shown in blue. The probability distribution of pitting for corrosion of steel bars in reinforced concrete. The pitting factors are important parameters of corrosion since they give an idea of the reliability of predictions of capacity from the point of view of the distribution type. The steel bar model contains a 250 mm corroded section along the bar, which was cut at intervals of 1 mm to form up to 250 microsegments. A microsegment is shown here. Alpha equals PL max divided by PL average. Beta equals PM max divided by PM average. Pitting factors alpha and beta. R0, the nominal radius of the steel bar. R mean, the minimum distance from the corrosion line to the center. PMM max equals R0 minus R mean. PM average equals R0 minus the square root of M1 divided by pi. And alpha equals PL max divided by PL average. PL max equals maximum PM max of the 250 microsegments. PL average equals the square root of eta times R0. Eta is mass loss ratio. Beta equals PM max divided by PM average. Dependence of pitting factor on mass loss ratio. When the mass loss ratio increases, the value of pitting factor alpha decreases and tends to stabilize, which indicates that the degree of corrosion along the longitudinal direction tends to be uniform. In this figure, the vertical axis shows pitting factor alpha and the horizontal axis shows mass loss ratio. When the mass loss ratio increases, the expectations of beta get smaller, which means the corrosion degree becomes uniform in the transverse direction. In the right figure, the vertical axis is expectation of beta and the horizontal axis is mass loss ratio. Thank you for your attention. Challenge number 7. If you like to challenge yourself, please answer this question in the comments down below. According to which ASTM standard are pitting and crevice corrosion resistance of stainless steel tested?